Okay, so there are no questions. So we'll move to the focus operator. So all the while, right, we've been assuming that this plot, this focus measure plot, right, that I've been indicating. So I've been assuming that. That there's some operator, right, which will act and give me a sense of sharpness. So this focus operator is something. So focus operators, in fact. Okay, so they will give you a sense of sharpness. In fact, right, I mean, these are other than this depth business, right, that I've been talking about. In fact, these focus operators are constantly being used in all your cell phones, by the way. So when it goes into that hunting mode, right, when you say autofocus, right, how does it know that something is in focus? How does it know at what lens setting, right, something ought to be brought into focus, right? How does it know that? So when you say autofocus, right, what it is actually doing is it is capturing a bunch of frames, just as we are doing here, but then it's capturing it very fast. Okay, we don't even see all of that, and we don't typically have access to those images, but you can do something to actually access them. But normally we don't get to see any of that. So it's, right, it tries to move the lens, and at that time it doesn't care about the parallax and all that, because autofocusing is not about estimating depth and all. So all that it does is captures a bunch of frames, moves your lens, captures a bunch of frames, and then it knows that, and then it runs a simple focus operator. Again, each company has its own way of trying to sense the sharpness, and then as it runs this focus operator quickly, and where does it run? Typically in the center. So it assumes that the central region is what you're interested in. So it runs right. I mean, a quick focus measure operator tries to get a sense of where things are coming into focus, so it knows that that's the lens setting that it needs to use. So this is called hunting. And in fact, many of these cameras, they have different ways of speeding up the hunting process and all. So there is a Panasonic 2017 model GH5 or something. I read about it somewhere, Lumix something. So that in fact claims that it is 100 times faster than the other cameras, because it uses only 2 frames to kind of lock on to the. It calculates depth actually. Okay, that one of the things that calculates. There's only 1D. There's nothing like a depth map. This computes the depth for the central portion of the scene, and based upon that, maybe, right, if time allows, I'll talk about it. Right? So I'm saying that other than this sense of depth and all, depth map and all that, which is maybe more involved, but these things are being constantly used. I mean, whenever you want to get a sense for sharpness and so on, but then nobody knows which operator is the best for what scene. Okay, that is right. Nobody knows. So there are all these people that have said that use this, but then nobody knows which one of them is the best. Okay, so I'm going to list down a bunch of these operators. Okay, we'll kind of go through them one by one, and you could use any of them. Okay, but there is no guarantee which one of them is going to serve you the best in a particular situation. Okay, so as you would expect. Okay, so one of the first things, the naive things would be what's called a pointwise operation. See, pointwise is normally undependable. It's like saying that you're only looking at that point and not even around it. Okay, so when you just look at a point, it is typically a grayscale value, and all these operators have to be simple. I mean, right? You can't have something that is very complex. Okay, that is running, which means that it is going to take time and so on. So if you look at these operators, they are very simple. Okay, they don't do anything fancy. Okay, so they do some simple things in order to get a sense for sharpness. So grayscale value, okay, is one, which is simply what we mean by that is simply, right, look at the intensity. Okay, but then this is seldom used. Why? Because of the fact that there is noise and so on, right? You would end up concluding something very, very wrongly, right? So normally not used, but this pointwise. This is the only point operator really. The rest are all kind of, they do use the local information. What is called a neighborhood. Okay, they don't just go by what is happening at that pixel. They also look at what is happening in and around it. So second is variance, but variance of course will also require you to compute the mean. Okay, and the mean, of course, you will again use a window. Okay, so variance of let's say, now I'm going to write this as x subscript. Okay, by which I mean that you are at some location x comma y. Okay, I don't want to every time write x comma y. So this x means that you are at a location. Okay, x comma y. And what you will do is you will do something like 1 by m square, where let's say m number of locations are involved, and summed over some z belonging to a neighborhood of, so this is like window of x. Okay, w of x is like the neighborhood of x, and then the value of the intensity, right, or value of the image at that z. So, z again, okay, z is again like some x comma y sort of location, but which is in the neighborhood of x. And typically these are all very clean neighborhoods, 3 cross 3. You don't use some fancy, irregular neighborhood and all. Typically regular neighborhoods, 3 cross 3, 5 cross 5 or something. F of z minus mu, where of course mu again will be the mean that we can compute as simply 1 by m of that neighborhood and square. Okay, so variance seems to make sense, because if something is coming into sharpness, then typically your variance will go up, right? Because your smoothness is less, and therefore variance makes sense to use. But then this is also not so very often used. Okay, but then this is more sensible. Energy of the gradient or what is called EOG. So this is like EOG again at x is given as sum over z belonging to, you can of course use all that 1 by m square and all and use that averaging. Okay, I may not write it every time. Doesn't matter because m is the same, so whether you use that or not. And then it does f square x z plus f square y z. Just adds the two. Okay, now this is normally a 3 cross 3 window. Okay, over which you are kind of taking these values, and this fx and fy, right? This is supposed to be a gradient along x, image gradient. Okay, image gradient along the x direction, and similarly, okay, fy is like image gradient along the y direction, and we need to have some kind of a discrete approximation for that, because you are on a discrete grid, right? Therefore, fx and fy and all, we need to have some operators that will be a discrete approximation of really a continuous differentiation, and all those exist. Okay, so we will talk about one, and when we talk about that, you will automatically know how these can be found out. Okay, so it simply means that you are computing this gradient. Again, right, this also makes sense, because if something is sharp, then your gradient will also be higher, because your transition is going to be higher. Right? Something is very smooth, then your gradient changes will also be less. Right? So these are all more or less intuitive. Okay, so what you or I would kind of think about. Then there is something called a tenigrad. This is based on something called the Sobel mask. If we do edge finding, right, at that time we look at what is a Sobel operator. This is a person's name, by the way, Sobel, and this is given as a tenigrad of x is equal to summation. So this is a Sobel operator. So this is a gradient computed using Sobel, and it's given as Sx f of z. Again, z coming from the window of x square plus. So the only change between the earlier one and this is that this explicitly uses a Sobel mask. Sobel mask is supposed to be better because it tends to add a kind of a weightage. Okay, when you do this sort of a differencing. Okay, so that is why none of these may really matter so much. Okay, because at the end of the day, it is the image quality or the image underlying activity that will actually decide. But okay, this Sx, right? So this will be a kernel like this: -1, 0, 1, -2, 0, 2, -1, 0, 1. So those 2 is that additional weight, because you're kind of looking for something around this. Therefore, you just give an added weight, right, along that row when you're doing an x gradient. And similarly, when you're doing a y gradient, you do like -1, -2, -1, 0, 0, 0, 1, 2, 1. I'll ask you something, right? As opposed to, right, when you saw a blur kernel, right, we said that it should satisfy certain things and it has certain interesting properties. What do you think is interesting about these two or these operators? I mean, del x. If I write it this way, what do you kind of notice as interesting? sum, yeah, they actually sum to 0, right? And why should they sum to 0? Huh? There is? Yeah, exactly, right. So what it means is, if you have an image, right, in which, let's say, right, things are totally smooth. Okay, so when you blur, that's what you expect, right? When you blur, when you're doing an averaging, right, what do? You actually bring all of them roughly to the same intensity, right? That's what averaging will do. You keep on doing repeated averaging, that's where you will head. So the idea is that if things are looking more or less the same, then your focus measure should be such that it should output a low value, right? And no, and only when things are rapidly changing inside a local region, that is when you want the right this FM to be high, the focus value, right? So it makes sense that if you have a situation where let's say, right, all the intensities are looking very similar, that means either there is very heavy blur, or it could also be that the image itself is like that, right? In either case, there is no activity, and therefore your focus evaluation value should be low, right? So these are right. So these naturally sum up to 0, okay, and that is the way they ought to be. Then there is something else that is called sum modified Laplacian. Okay, this is what is most commonly used, by the way, and this is what Laplacian. And I'll tell you why it's called SML. Okay, and this is known to work right, pretty well, in the sense that not any many mathematically optimal or something, but this is known to work very well. So this is like fx. So if you look at Laplacian, right, if you have a 2D grid, a Laplacian is like fxx plus fyy, right? So it's like dou square f by dou x square plus dou square f by dou y square. Okay, this is what is actually a Laplacian. So this is called a modified Laplacian, and there is also some, right, tagged along. So I'll explain all that to you. So what this SML operator does is, right, it works like this. SML of x is given by, again, z belonging to w of x, then fxx at z bar and fyy mod. Okay, so the mod is taken, and then you take the mod of each of these second derivatives, and then you add them. And of course, as you keep going higher in the order, right, you will naturally believe that these have to be more sensitive to any kind of changes in the intensities. But at the same time, they could also become more sensitive to noise, right? That will also happen. But then overall, it looks like this is a good sort of a compromise between the sensitivity that you need versus the ability to sort of handle noise, okay, to kind of say counter noise. And by the way, right, there are some very interesting papers for those of you, right, who are interested. I think 2 years ago or something, there's a group from Hong Kong, right, that showed that what is called, I think the paper title is, if I remember right, it's called just noticeable blur. Okay, just noticeable noticeable blur. I think that is how it is. That is how the main this one. It has a title like that, just noticeable blur. And there they show that, even with a kind of regular camera, right, if you take an image to your human eye, it looks like, right, everything looks like it is focused. But it turns out that, there is a subtle sort of a change in blur, differences in blur across the image that can all act as a cue for depth, and these guys do a fantastic job of actually bringing all that out. So why I'm saying that is these operators and all, right, of course they don't do it using these focus operators, they use something else. But I'm just saying that this is what you want from these focus operators. You want them to be extremely sensitive to any changes in blur, because that is what will help you tell where the sharpness is actually exactly happening. Okay, so anyway, for those of you, this was some CVPR 2017 or something, right, or maybe even a little older than that, 16. So, but it's amazing. If you look at those images, you don't, right, to your naked eye, it looks like they're all pretty much in focus. But then they show that it is not the case, and you can actually start inferring depth of a scene just from naturally captured images with a cell phone. Okay, and okay, right. I'll just expand on this operator, right, a little bit. So So this some modified Laplacian, right? So it's called a modified Laplacian for this reason that a Laplacian would have simply summed up, right, fx, I mean, would have been simply a sum of fxx and this fyy, whereas in this case, right, it takes fxx but then takes a mod of that, right, and fyy takes the mod and then sums up the two mods. I mean, that's the way they call it. That's why they call it some modified Laplacian. And if you think about it, right, I mean, so suppose we wanted, a discrete approximation, just to start with, right, we'll just do it for this case, fxx, right, what it will look like. So these are all standard things, but we'll just do it here. So a discrete approximation, because finally, right, we need some kind of a kernel that you want to run on the image, right. So a discrete approximation for fxx and fyy. Well, whereby f I mean the image, okay. So I don't know, we've been calling g as the image, so you can look at it as gxx, gyy. Okay, now, all right, yeah, g, I think g is what I've been using, right, all along. So I'll say g, gy. No, in those expressions, I think I've been using f. Doesn't matter, okay, use f for g or what. Okay, fxx, fyy. All right, so fx, right. So the normal, the very standard approximation is take it as f of x plus 1 y minus, say, f of x comma y. I mean, there are various approximations. One very standard way is f of x plus 1 minus f of x comma y. Okay, and which then means that if you are looking at fxx of x comma y, then you should kind of be looking at fx of x plus 1 comma y minus fx of xy, right. We are looking at fxx, but then fx of x plus 1, right, it will turn out that from the first one, it will turn out as f of x plus 2 comma y minus f of x plus 1 comma y, then what is it, fx of x plus 1, right. So fx of x plus 1, x plus 2 minus, and then minus fx of xy, that is f of x plus 1 y minus, no, plus f of xy. Okay. So which then means that you get something like f of x plus 2 comma y minus 2 times f of x plus 1 comma y plus f of x comma y. Okay. Now, since right, this is centered about x plus 1 and not about, so like I said, right, you want to wait at x comma y and not at some other location, right. You're looking at finding fxx at x comma y, whereas this is putting more emphasis at actually x plus 1 than x. So therefore, what is standard practice is to replace x by x minus 1 in this expression, so that what you end up getting is x of x plus 1 y. So replacing x by x minus y in the above expression, right. So that is purely done in order to give more weightage to x comma y, right, where you are trying to evaluate the second gradient, minus 2 times f of x plus x comma y plus f of x minus 1 comma y. So right, this is in fact a very standard. So if you try to write it down in a kind of a 3 cross 3 form, right, what will mean is you'll have a minus 2 weight here, you'll have 1 here, and then 0 0 0 0 here, right. So this will be something like dou square by dou x square, or what I call as fxx, and then along y, right, you can similarly show that if you do the same thing along y, you will end up with this, what is it, 1 here, minus 2 here, 1 here, and 0 0 0 0 0 here. Okay, and a standard Laplacian, right, when you write the dou square f, which is a Laplacian, that is fxx plus fyy. Okay, a Laplacian typical symbol is this, and then if you add these two kernels, right, then what happens is, what you will end up getting for a typical Laplacian is minus 4, 1 1 1 1, and then 0 0 0 0. Okay, so this is a standard sort of a discrete approximation for a Laplacian kernel. But what we want is actually a modified Laplacian. Okay, but this is what is really a Laplacian kernel. The simplest approximation that you can make for a Laplacian kernel. So again, this will also add up to 0 and all that, okay, because this is also supposed to give out a value which will be low if all the intensities are similar looking, and high if there is a lot of activity. So all of that, this will also follow. Coming back to that modified Laplacian, right? So what it actually means is that if you go back to that thing, right? So what you had was this one, right? So where is that? So if you see here, right? So you say fxx, right? So fxx. So what it will mean is you'll replace it with this kernel. It will be -2, 1, 1, and then 0 elsewhere. And then so this will be a kernel that will be. So the way right they operate is like take these individually and then operate on the image to get the gradient and then take the absolute value. Then again take this kernel, right, operate it on f, which is like doing simply a convolution. Operate it on f and then get the second gradient along y and take the modulus of that and then add the two. Right. So ideally, you will get one array coming out of one array that comes out of this, another array that comes out of this. You are just taking the mod of course. After you take the mod, you will get these two arrays, and then you're just adding up those values to get another array that is supposed to give you the value of SML at all locations. We'll talk about the implementation, a little later. Okay. I mean, so there are so the way we actually implement is like we don't go like take one pixel at a time and then do this. Okay, we would rather operate on the whole grid at one go. Okay, because doing a convolution is fast. So just operate in one go, get all the values, and then do all these local things. Then there's one more operator. Let me also write that down. This you may be familiar with, what is called the Laplacian of the Gaussian. What's called log of x. So summation again z belonging to w of x, log of, anyway, so I'm not writing this, so for those of you who are interested, you can find out again it's again sort of a convolution. So what it will mean is, did we talk about how to, I think right, we did that, no? So if I gave you a sigma, then we know that then we know how to actually have a kernel for that, a discrete kernel. So Laplacian of the Gaussian is like you have a Laplacian kernel which I showed you just now, and then you have an image. So log of the Laplacian of the Gaussian is like you take the Gaussian kernel, blur the image first with that kernel, and then apply this operator Laplacian, which is then get a convol. So first is a convol with the Gaussian. So it means that it is going to probably blur that image a little bit, and then on that you operate a Laplacian kernel. There are also direct kernels that can give you the log itself directly. But the simplest way to think about is blur first with actually a Gaussian and then follow it up with this Laplacian kernel. You know how a Gaussian kernel can be written. Similarly, you know now how this Laplacian kernel can be written. So those of you, right, who just want out of interest to do something like this, you can still go ahead. I'm not writing those expressions here because simply means one kernel for the Gaussian followed by another kernel for the Laplacian. Then there is something called energy of the Gaussian, energy of Laplacian. Energy of Laplacian. So this is called EOL of x, and this is given by summation z belonging to w of x, then fx x of z plus fy of z, the whole square. Okay, so if you see, right, this is not the same as the modified Laplacian, where you took each one of them individual mods and added up. Here it's like you're just taking like fxxz plus f4. Okay, time. Okay, so all these are, and in all of this, right, we do not know which one of these, right, nobody knows for sure which one of them is most ideal to use and so on. Let me talk about the sum part. So it's like this, right? So modified Laplacian, because of the fact that what you do you will take every frame, right, and act, let's say your operator dou square by dou x square, okay, which is this kernel that I wrote down, okay, for a second derivative. You simply do a convolution with each frame. Okay, output will be another frame, right? So you'll get again another stack of frames, right, if you do a convolution. Similarly, you'll use the same frames, and then you will also do a convolution with dou square by dou y square, which is again another kernel that we had, right? Whatever 1 minus 2 1, and then the other case is 1 minus 2 1, right? So you convolve, and then again you will have, let's say, one more stack. Correct. Now what you do is you take the modulus of this, you take the modulus of right, all these values, because that is a way to do it fast, right? You don't want to travel one pixel at a time and all. So if you take this modulus and then if you add them, then you will get one more array, okay, or one more stack, which will have all these ML values, right? That's called like ML of, if you want to call f of xy, right? Then all the modified Laplacian values are all actually sitting here, correct? And the sum modified Laplacian, right, looks like this. So when we say sum modified, right, what we really mean is this. Why this not going? So when you write SML, okay, suppose I say at f of x comma y, because finally, right, I want at some x comma y, what is the sum modified Laplacian value? Then what I will do is I will take it to be ML. Okay, now this will be a double sum over, let's say, I is equal to x minus n to x plus n, and j is equal to x minus n to x plus n. I will tell you what this n is, and then what you have is ML of g of f, right, ML of I of f of I comma j. So that's why it's called a sum modified Laplacian. So what it is saying is, see, you have this array, no, right? You have the stack that you got, which is actually ML of you say f of xy, at all xy you have the values now. So what it does is, in order to be a little more robust to some noise and other things, so what it is saying is, it'll actually it'll kind of add up the values in and around your x comma y. So for example, if you take n equal to 0, then it means that it simply takes the ML value right there and then uses it as the value for say SML. But normally what is done is, we will take, let's say, n equal to 1 or 2 or something, because 1 will mean that it is looking at kind of, right, a 3 cross 3 neighborhood, adding up all those values. Whereas if it is n equal to 2, then it will mean it's looking at a 5 cross 5 neighborhood, adding up all those values in order to tell that. But then the point is, right, you can't make it too big, because you have a depth that is actually varying, and therefore, right, it won't make sense to take to kind of take a very large neighborhood. So you can either go with n equal to 1, which is what is standard. Typically go up to n equal to 2 or something, but not beyond 5 cross 5 and all, because otherwise you will end up smoothing your say depth plot, right? So this is again this is another way of sort of, right, implicitly accounting for noise. Okay, so if there is some variations that are kind of that you are not able to pick up, or let's say your let's say red D bar itself for some reason, okay, if you feel that just trying to get values at one location is going to be a problem, then you could actually look at a small little sort of a neighborhood, right? That's why it's called sum modified. So the sum is coming from this sum, okay, sum, and then some of the modified Laplacian values. That's what it means, okay, sum modified Laplacian. And then what this will mean is that once you have the sum modified Laplacian value, you can actually plot it for right, every x comma y now, right? You just traverse through that stack, and you have the SML at x comma y from coming out from every stack, and then you have that FM plot. Then you can actually do this one, a Gaussian interpolation. Then you can get your D bar, right? So if you use one operator, now the point is, right, I mean, who knows which one is the best? I mean, how does one? So there are a few ways out of that.